Hypothalamus Artificial Intelligence, HI. It presents companies in the process of digital transformation, its offer of professional services and the supply of algorithms of highly complex multi-problem mathematical models. These services are called Oil and Gas Industries Enterprise-Wide Optimization, Oil Pipelines Optimization. To provide these services, HI is supported by its business partners, GAMS, IBM and TD SYNNEX, all of which are producers of artificial intelligence technologies. HI is a company at the forefront of high-performance artificial intelligence. Oil Supply Chain Optimization. The oil and gas supply chain is made up of 4 links: upstream, midstream, downstream and retail. The links are connected by multimodal transport networks. The oil industry includes global processes of exploration, extraction, refining, transportation and marketing of petroleum products. The largest volume products in the industry are fuels, natural gas, fuel oil, and gasoline. However, petroleum is the raw material for many chemicals, including pharmaceuticals, solvents, fertilizers, pesticides and plastics. The table, elaborated by IBM, shows a resume of the optimization solutions for oil and gas enterprises. The distribution chain of petroleum products begins in refineries and ends at the sites of consumption of different types of products. Optimization solutions in the transport chain of petroleum products can be classified by their hierarchy: strategic, tactics, and operating. Several of these applications will be discussed below. Hierarchical coordination of planning tools. It is traditional to organize decisions hierarchically into strategic, tactical and operational. The operational decisions are divided into the scheduling and advanced optimal control. However, due to the technological progress generated by Industry 4.0, mainly in relation to smart metering systems, nowadays we can talk about a new type of online optimization modeling, real-time distributed optimization. From the point of view of mathematical modeling, hierarchical levels are intertwined and coordinated through the boundary conditions in time, and common modeling that can be shared. The modeling strategy of HI is that all models of a decision support system can communicate with each other. HI Oil meets all the software solutions developed by HI in different areas of application of mathematical optimization models, oriented to planning and to scheduling operations, in different business of the petroleum product supply chain. Oil Enterprise-Wide Optimization integrates mathematical models for each of the links in the oil supply chain, in such a way to management the planning of the supply chain with a holistic vision. The design of HI Oil AWO was the result of work done for a multi-business oil company. The union of models, and their coordination, forms the hypothalamus of an oil enterprise. The current computational power allows to model detailed the supply chain, considering individually all the systems that compose it. This allows to visualize all the existing bottlenecks, and that affect the maximization of economic gains. All models developed by HI, to support decisions in the oil industry, are interconnected trough and information system. In this way the construction of artificial hypothalamus is a question of joining the equations that make up the different models. Oil Transport Systems Optimization corresponds to a general model, common to all types of oil products, raw, refined, natural gas and biomass, which represents the process for a specific system, including particular equations when this is required. It considers 2 types of transport modes: pipes and multimodal vehicle, like vessels, barges, train tanks, and/or trucks tanks. The integrated transport system can be conceptualized as the junction of pipe and vehicle routes, which interconnect multiple terminals, which are the places where are connected the different installations. Each transport media is modeled independently. System connectivity is done through the terminal, a node, that corresponds to a point in the space in which at least 2 installations are interconnected, such as oil fields, plantations, oil refineries, biorefineries, port, consumer centers, and thermal plants. The table presents a summary of the mathematical models developed by HI for oil and gas transport optimization.
Los cerebros artificiales, integración de inteligencia artificial y la programación matemática. Son el resultado de la investigación de HAI en metodologías de modelado matemático disruptivo para la industria 4.0. Y son la base de la arquitectura computacional de nuestra propuesta. Para mayor información, se invita a los interesados a ver el video. Artificial Brains, Artificial Intelligence and Mathematical Programming Integration. Esta información hace parte de la presente propuesta.
Numerical simulation model of the digital twin. It corresponds to the physical model that exactly reproduces the behavior of the piping and pump system, that is, the flow of different types of products in the different sections of the pipes, and of the operating conditions in the pumping stations, for each pump configuration pattern, in series and or parallel, for each type of product, for any pump speed. This model is integrated as physical model to predictive analytics methodologies, specifically the Kalman filter, and basic model to generate the approximate model that is part of the optimization models. The numerical simulation model produces matrices, or tables, that are the reference of the exact operation of the piping system and pumping stations, and these tables numerically represent functions of the energy consumed as a function of pressure, flow rate, product type, DRA injection, ambient temperature, etc. Validate and correct advanced analytics models, mainly optimization models. State estimation, models the prediction of estimation of the variables that represent the state of the system. These can be pressure, flow, RPM, roughness, density, etc., and physical model parameters, estimation of the parameters involved in the equations that represent the physical system, and which are subject to uncertainty. It is considered that the appropriate methodology is the Kalman filter, FK, including some of its variations and extensions. FK is, perhaps, the oldest, and most robust, methodology of hybrid predictive AI. The numerical simulation model can be used to generate synthetic operation samples, as it is assumed to correspond to the exact representation of the system, and thus enrich the database, very useful in the case of young systems with few historical measurements. Prescriptive analytics. To optimize are required the following models. The operation, dispatch, of the pipeline, at least 1 or 2 days in advance. This implies a real-time operating model, whose planning horizon is divided into periods of hours, fractions, and which can be redispatched at any time, and the transport of hydrocarbons in relation to nomination, DRA dosage, energy consumption month by month. This implies a short medium-term tactical operating model, whose planning horizon is divided into periods of weeks, fortnights or months, and that it serves to adjust the pothole program, prior to the dispatch of the polyduct. It is considered that the appropriate methodology for these models is mathematical programming, Tambien conocida como exact methods. The other optimization alternatives are discarded by not be exact, may produce unfeasible solutions, and they don't guarantee to get the optimal solution, they leave money on the table. The results of the models, mainly the real-time ones, must feed the databases of the SCADA system, or distributed control. The image presents the IT architecture of the proposed solution. The mathematical models will be analyzed later. The high methodology involves linking predictive and prescriptive artificial intelligence methods, to give rise to decision-making artificial intelligence. Pipelines energy modeling. Predictive analytics models, forecasting. Based on hybrid models, model-driven plus data-driven, supported in state estimation methodologies, more specifically improvements and variations of the Kalman filter, KF. Overall, the minimum functions of these models are smoothing, filtering and forecasting of the viscosity value of the crude oil transported in real time at any point of the pipeline, taking into account that, on a daily basis, laboratory tests are carried out to establish the viscosity value that is being transported. This actual viscosity data is confirmed a day after the shot by analysts. Smoothing, filtering and forecasting of the viscosity value of products in real time, assuming that an inline viscometer is available. However, the measurement of this is not exact, but it maintains precision, and allows you to verify the trend of the measurement. Identification of the operating periods during which, due to the quality of the product, density and viscosity, the dosage applied affected the transport of hydrocarbons. Given the characteristics of KF, smoothing, filtering, and forecasting of the value of the pipeline's operating variables at any point, using the pipeline's physical model, and smoothing, filtering and forecasting of the value of pipeline parameters, e.g., roughness, slope, etc., when it is considered that these may be subject to uncertainty. As a general rule, it is considered appropriate to use an extended Kalman filter, or a dual Kalman filter, to simultaneously estimate state variables, and the parameters of the equations. Data-based algorithms only consider the database of observations, historical or synthetic, to determine the dynamic prognosis of the physical process. Normally, the related professional is a data scientist. Model-based models are based on the numerical simulation model, which must be fitted by means of algebraic expressions, to be expressed as a system of stochastic differential equations, or finite differences, or finite elements. This requires an expert in the field of interest, in this case fluid mechanics, mainly in the transport of petroleum products. The integration of the two approaches gives rise to hybrid predictive analytics, which can be considered as the appropriate method, that takes advantage of the mathematical knowledge of the physical system, and historical information. The most well-known method, and most used, for more than 65 years, is the Kalman filter. The state estimate describes the system based on state variables, characterized by discrete, empirical probability distributions, and dynamic, empirical, probability distribution functions that evolve over time. Forecasting, predictions about the future, and filtering, predictions for the present. In a system under uncertainty, correcting the past may be just as important, if not more so, than forecasting the future and estimate the present. Examples of applications of the Kalman filter in pipelines are system monitoring, parameter calibration, leak detection, and maintenance following PHM methodologies. Though interested in learning about Kalman filter's applications in the petroleum industry, we invite you to watch the video series Oil and Gas State Estimation Using Kalman Filter. In the case of pipelines, the main applications are estimation of the operation profile, leak detection in pipelines, Kalman filter applications in oil and gas pumping stations, Kalman filter applications, prognostic and health management, PHM, maintenance in pipelines, optimization models. Planning on a monthly level. It determines operating rules, practices, that are optimal when the planners want to operate based on fixed operating rules over a period, of the order of months. The results of this model are as follows. Pothole cycles, order of the type of products, e.g., crude field 1, crude field 2, crude field 3. This constitutes one pothole cycle. The number of pump cycles, to have an optimal line full. The size of each pothole. Volume of each type of crude oil within the cycle. The expected DRA dosage for a certain pothole program, and optimal setting of pumping patterns for a certain pothole program. Based on the above results, it is possible to plan the consumption of resources in the short-medium term, and if necessary, program the operation at a daily level, given a set of potholes that you want to transfer along the transport system. Daily scheduling. It determines the optimal operating conditions for a planning horizon of the order of days. Specifically, it is expected to define operation schedules up to 3 or 4 days in advance. The results of this model are as follows. Pumping plan at each pump station, optimal pump configuration pattern, for the pump stations, and RPM at each pump. Contribution of DRA at injection points, in each period of the planning horizon, and the flow and pressure variables along the pipeline, which can be visualized in the pipeline digital twin. The two models share equations and processes and differ in the specific characteristics of monthly, tactical, and daily, real-time, planning. The objective function of the models may vary according to the criteria of the decision maker, as well as minimize cost of operation, minimize energy consumption, and maximize oil products transfer. The models, together or individually, can be used to support other decisions related to the operation of the transportation system. For example, supporting the ATP, available to promise, decision to accept, or refuse, transport operational volumes for customers who request it, without having a prior agreement. To solve the mathematical problem of optimizing prescriptive analytics of a system, several approaches can be used. These are mental models, intuition and goodwill, simulation, physical model plus human reasoning, meta-heuristics, smart rationing, machine learning, experiences, best practices, and mathematical programming, physical model plus optimization mathematics. Of the above alternatives, the only one that can guarantee optimal solutions is the one based on mathematical programming. For many leading companies in the production of advanced analytics technologies, such as IBM, stochastic optimization, and deterministic optimization, are the analytical technologies that produce the greatest competitive advantage, and that provide the greatest ability to handle complexity. For this reason, it is proposed to use mathematical programming models to solve optimization problems. In decision-making, artificial intelligence mathematical programming may be considered the best of the breed. Pipelines planning and scheduling. Compared to other transportation modes, like road, railroad and vessel, pipelines are the safe stand most economical way of conveying petroleum products over long distances day and night. During the last 2 decades, the operational multi-product pipeline scheduling has gained increasing attention. The problem of optimization of pipelines involves safe, reliable and economical operation, in which, for each moment of the planning period, the flows, pressures and configurations of the pumping stations must be determined, according to the different types of products that must be transported through the pipeline network. The goal of the operation moves between 2 criteria. Minimize energy consumption, environmental criteria, which is important to preserve the sustainability of the planet. Minimize the cost of energy, economic criteria, which is important in energy markets where rates change throughout the day. On the other hand, the technical operating conditions, hydraulic conditions along the pipelines and at the pumping stations, must be respected regarding the flow of multiple, different potholes that must flow through a network of pipelines that involves the synchronization of multiple sections that connect several production fields, refineries, and ports. The transportation system has 2 fundamental components, the pipeline system and the pumping stations. The planning and scheduling of transport operations of products through pipelines, oil and refined products pipelines, aqueducts, gas ducts, and mineral pipelines, is done using 3 coordinated models. Sales and operations planning, SAND-OP, determines the total optimal volumes transferred during the planning periods, regardless of the sequence of products in the pipeline. Scheduling operations, SCH, determines the volumes and the sequence of batches to transfer during the planning period, whereas the volumetric planning established in the previous model. Real-time optimization, RT, determines transfer speeds, pressures discharge, and pumping stations operation patterns to meet the scheduling of tenders. The equations in the 3 models are virtually the same. The difference is in the way the energy losses are calculated, and the operations of the pumps are handled. Discrete time and continuous time modeling. There are 2 alternatives for modeling operations scheduling, discrete time models, and continuous time models. Continuous time modeling coordinates and detail the beginning and end of all activities that are part of an operations plan. The conceptualization of modeling is generic, in the sense that it can be applied to any programming of detailed operations of a production system. The effort in modeling is greater than in discrete time and is less known by mathematical modelers. Its direct application is real-time models. Discrete time modeling divides the planning period into periods, usually of equal duration, and determines the average conditions in which the production system must operate. This modeling is better known, and traditionally is used for tactical planning. If greater precision is required in the results, the duration of the periods must be decreased, which increases their number, which entails problems of greater dimensionality. Any of the above methodologies may be useful in solving real problems. The suitability of its use is determined only after a detailed analysis of the matrix structure of the optimization problem is performed. The real-time models includes nonlinear modeling that determine the amount of energy consumed based on the flow of products in the system. In aggregated models, when multiple types of products can be transported in the pipeline, the total transport time must be divided into the time used to transport each type of product at different transfer rates. To represent the flow of energy through the transport system, the following constraints should be considered. Energy conservation in the ducts and nodes of the system. Minimum pressure limits, or compression, at the outlet of the ducts, and pressure, or compression, minimum input to the ducts, depending on the type of connection between the operational area, node, and the duct. In the real-time model, a detailed hydraulic system is available in the pump operation model, for each type of pump in the pumping system, and each link in the pipeline, for each type O product, O crude. This ensures the feasibility of the results. The real-time model can handle differentiated electricity costs by time of day, or by load block, using this way to take advantage of low rates, or low marginal costs, in periods of electricity low load. The hydraulic characteristics of the flow depends on the type of oil product that is moving along the pipeline, and the blending of these crudes along the segments of the pipelines. The three types of pipelines exists: oil pipelines, they transport crude oil from oil fields and ports. The polyducts transport refined oil products, like gasolines, diesel, jet gasoline and others. A gas pipeline is a pipeline that allows combustible gases, natural gas, liquefied petroleum gas, to be transported on a large scale and over a long distance. The optimization mathematical models for pipelines transport system can be used with one of the following objective functions: minimum power, minimum cost, and maximum flow. Optimization strategy. The problem-solving methodology must speed up the optimization process. The chosen method by High is based on problem breakdown for the different periods that make up the planning horizon. The synthesis of the behavior of pumping stations by means of a non-convex hull for variables that synthesize their optimal operation as a function of pressure, P, and flow, Q, for a given type of product associated with the BT batch, and coordination of the optimal solution according using a Lagrangian coordination scheme. The purpose of this is to iteratively solve significantly simpler problems that allow to solve the original problem in significantly shorter computation times. After several analyses and numerical experimentation with mathematical models that represented the detailed problem, the following design principles are reached in order to make the solution of the problem viable as specified. Split and decompose the problem into multiple problems of lower dimensionality in order to obtain the solution based on an iterative process. Maintain the format of the problems as linear or quadratic to take advantage of the solvers specialized in this type of problems, and perform pre-processing of information in order to accelerate the solution of the problem, offloading to the optimization model unnecessary repetitive calculations. Pumping stations modeling. In the oil industry and other industrial processes, pumps are divided into two general classifications: variable head pumps, centrifuges, and positive displacement pumps. Screw variable head pump types include centrifugal and turbine pumps, while positive displacement pumps include reciprocating and rotary pumps. The screw pump is one of the commonly used rotary-type pumps in the oil industry, and are mainly used in low-flow operation, where the efficiency of a centrifugal pump would be very low. On the other hand, the versatility in handling high-pressure heads makes the centrifugal pump the most used in industrial applications. The effect of a pump on a system is to increase total energy. The action and operation of a pump is defined in terms of its characteristic curves. These curves relate the capacity, flow, of the pump, in volume units per unit of time, versus the discharge pressures. The equation that represents this ratio is obtained from the characteristic curve of the pump, which is provided by the manufacturer. This curve is generated for a pump rotation speed and for a characteristic viscosity of a reference product, usually water. This implies that, to determine the coefficients of the actual pumping curve, it is necessary to adjust the coefficients of the characteristic curve, based on the viscosity of the fluid that is pumped. If the pump rotation speed changes, adjustments must also be made to determine the actual operating conditions of the pumping station. When a defined flow is required, and knowing that the system curve varies, it is necessary to affect the pumping curve, and thus find a new point of operation that meets the safe flow and pressure needs for the system. The pumping curve can be affected by different shapes, each pump that is variable speed motor that can affect its pumping curve, by changing the rotation speed. The figure shows 3 pumping curves for different rotation speeds, of the engine associated with the pump, usually measured at RPM. The curve presents the relationship between energy consumed, or outlet pressure, and output flow in a pump. The relationship is exponential, implying diseconomies of scale in energy consumption as a function of flow. In theory, the pump has no limit in flow, but for an infinite flow rate, it would require infinite energy. On the other hand, it is normal that there is a minimum flow rate, so that the pump begins to operate. The curves depend on the product transported. To the extent that it is heavier, denser, more power is required for the same flow. This applies to petroleum and petroleum products. That is, the curve depends on the API grade. A pumping station is composed of multiple pumps, usually of the same type. While the atom of the system is the pump, it is necessary to analyze the behavior of the station as a machine, whose function is to pump a product to a certain transfer rate, and at a given pressure. The pumping curve is determinant of the operation of the pumping stations. A way to affect the pumping curve is by setting up pumping pattern, at a pumping station where there are multiple pumps. Configuration shapes are 2. In parallel, and in series. When more than one pump is configured in parallel, the system receives higher flow rates, the sum of the individual flow rates of the active pumps, at the same pressure level. When 2 or more pumps are configured in series, the system receives greater pressure, the sum of the individual pressures of the active pumps, at the same flow level. There are multiple operating patterns to configure the pumps of a pumping station. Its discrete character implies that selecting the more convenient corresponds to a combinatorial mathematical problem. An aspect to consider is related to the type of pumps and the operating restrictions of pumping systems. The diagram shows the case of 2 identical pumps that require a minimum flow rate for their operation. In this case, the first pump must meet the operation between min y2 min minus an infinitesimal value. Starting with d2 min, it is optimal that the 2 pumps operate simultaneously. If the pumps are operated in sequence, as much energy as possible will be expended. This behavior involves a discontinuity in the optimization model which must be handled carefully. The behavior is different with fixed pumps, as they cannot regulate the minimum flow rate, and must lose energy in a dissipating valve, that allows excess energy to be released. The 2 cases involve non-convexities in the optimal consumption curves. The graphic shows the optimal energy consumption versus flow rate for 20-station pumping mix oil, for different pressure levels. The optimal energy consumption is the result of an optimization model. The graphic shows the optimal energy consumption versus flow rate for the XX station pumping heavy oil. The graphic shows the optimal energy consumption versus flow rate for the 30th station pumping heavy oil. It can notice the flows that force the ignition of a new pump, which generates a discontinuity in the curve. This complicates the solution of the problem, since for such flows, the curve has 2 values. A fundamental aspect of optimization models is the definition of the feasible zone. In most problems this is not complicated. However, in the case of pumping stations, it is necessary to carry out a detailed analysis. The greatest complexity is generated because the feasibility zone depends on the configuration of the pumping station, making the feasibility zone a disjunctive constraint. The graph presents the feasibility zone when the operation pattern is in series. The graph presents the feasibility zone when the operation pattern is in parallel. The graphic shows the feasibility zone of 20 pumping station, operating in parallel, pumping mix oil. Given the non-trivial form that gives rise to calculations, to represent the pumping feasibility area, the pump curves can be replaced by an algebraic function based on parameters, estimated through a least squares model. The polynomial function, or directly the empirical function, may be approximated by a piecewise linear function. For each pattern and product, the feasibility zone is linearized, based on the hyperplanes that support the continuous feasibility zone. The graphic shows the feasibility zone of 20 pumping station, operating in parallel, pumping mix oil. Now, the graph includes the linearized feasibility zone for pumping heavy oil. It is easy to notice that the area of operation for pumping heavy crude oil is more limited than for crude mix. The graph shows the maximum limits set by the extreme pumping patterns, which are assumed cover the remaining pumping patterns, and it defines the non-convex feasible zone for the pumping station operation. If the restriction is viewed as disjunctive programming, it has two convex disjunctive zones, since the pumping patterns is parallel, or is serial, but not both. This seems to be the most appropriate, from the point of view of mathematical modeling. The above feasibility zone must be intercepted with the restrictions imposed by the pipeline, usually maximum limits on flow and pressure. The graph includes the limits in flow and pressure, due to the pipe. The rectangle determines the feasibility zone for the pumping of mix oil. This indicates that the limitations in the pumping of mix oil are due to the pipeline. In the case of heavy oil, there are limitations due to the pipeline, and due to the pumping station. The operation of a station is determined by the following decision variables: pump configuration, in series or in parallel engine speed, RPM, and flow rate and pumping pressure. The configuration of the pumping stations is a central part of the decision-making process as, depending on the pumping pattern, the combined action of the patterns make possible to meet the flow pressure demand in multiple ways. The optimization requires a detailed hydraulic model, at the level of each type of pump used in the pumping system, and for each type of product being pumped. Considering the integral optimization of the entire pipeline, using large-scale optimization methodologies, partition and decomposition, the operation of each pumping station must be optimized through a mixed nonlinear programming model MILP, that minimizes the amount of energy required to dispatch a batch QP, for each type of oil. Associated with each point of the grid, the following data is stored in an optimization database. The optimal consumption, the operating pattern that produces it, and the dissipated pressure in the valve, unused available energy, and the RPM of the variable speed motors. The problem of determining optimal energy consumption in a pumping station is a relatively simple problem, but complex to solve, due to its combinatorial character. The image shows the grid of optimal operating policies for any pumping station of the system. To build it, the flow and pressure are discretized, and the problem of optimizing the operation of the pumping station, for each QP pair, for each product that flows through the station, is solved. To obtain a continuous solution, a convex linear combination is used, based on the 4 points that limit the polygon to which the solution belongs. It is an approximation. This process works well for the case where all 4 points use the same pumping pattern. If this is not the case, it should be analyzed how to resolve the situation. The grid corresponds to a hull, convex or non-convex, which represent the optimal solutions of the operation of the pumping stations, as function of the product, the pressure and the flow. If the envelope is convex, its incorporation into other models generates linear constraints. If it is non-convex, it implies the inclusion of binary variables, and will generate an MIP problem. The integrated optimization of pipeline systems requires that all the pumping stations must be considered jointly. For real systems, it becomes a high complex mathematical problem. For this reason, it must be faced using large-scale optimization methodologies, based on the partitioning and decomposition of the problem. The monolithic approach for oil pipelines optimization seems to be an impossible way, since the combinatorial character of the problem can make it impossible to solve in reasonable times. The first step to the decomposition of the problem is the generation the convex hull of all pumping stations. This process involves extracting from the monolithic model the model of the pumping stations. Using this model, convex hulls will be produced. This process involves extracting from the monolithic model the model of the pumping stations. Using this model, convex hulls will be produced. The results of the process must be stored in a database for later use in the pipeline system optimization model. The integral model must incorporate the equations that allow working with the convex hull to determine the flow and pressure for each product that flows through the piping system. The process of generating the convex hull can be done offline, prior to the use of the optimization model. If the APIs of the products are constant, as in the case of the refined products, the convex hull can use me for multiple runs of the optimization model. When it changes frequently, new convex hulls must be generated as products with new APIs appear, as is the case with crude oil. Pipelines energy modeling. A pipeline consists of sets of lines. The lines join two main nodes of the pipeline, pumping stations, and product terminals where there are storage tanks. Lines are composed sets of sections that join nodes. Each section has its own physical characteristics: slope, rugosity, thickness, length. The main nodes are characterized by the industrial infrastructure located on the node. All nodes are linked to a geoposition in the terrain. The batches begin to flow along the first section of one line of the pipeline, and must therefore be linked to the line through which they enter the system. The matter and the energy continuity equations must be met on all sections and nodes. The above concepts should be related to the operation of the transport system, using variables that determine for each period the position of the batch, which may be occupying several sections of one line, or several lines. The possibility of shutdown of the system, non-operation, zero flow, or of a pumping station, is also considered as decision in the model. In general, the study of pressure loss in a duct system indicates that there are three effects that produce the pressure drop: friction, gravity and acceleration. The most important effect for the behavior of pressure losses is that of the operating flow, which must be added to the pressure losses due to gravitational action and friction, which depend on the density and viscosity of the fluid. The acceleration effect in many cases is assumed to be negligible. As fluids of different characteristics, viscosity and density, enter the pipe, the work to be performed for transport changes, represented by the required pressure. This can be viewed graphically using the pressure loss representations as a function of the flow, called system resistance curves. These curves reflect the behavior of the pumping head required for a given flow rate. The pipeline height profile is a determinant of the energy required to transport a certain volume of a specific product, at a certain transfer rate. The pipeline height profile is a determinant of the energy required to transport a certain volume of a specific product, at a certain transfer rate. The energy losses in the sections depend on their characteristics, the type of product, and the transfer rate, or flow. They are independent of the profile of the pipe. Energy losses as a function of flow are exponential. The energy generated by the pumping stations provide the energy required for the transport of the products, to the extent that the energy that is in the pipeline is consumed. The energy profile in the pipe must always be positive, so that the product can flow. The image presents the variables used in mathematical modeling, including their description. Integration: the modeling of pumping and pipeline flow. There are multiple topologies to connect the pumping system to the pipe system. For real-time operation, this connection is very important. For tactical planning, it is less important, and may be approximated. The image presents the variables used in the mathematical model. The description of the variables is presented in the image. The image shows the synchronization of products injection in a pipeline. These can enter the pipeline in multiple ways, which must be able to be represented in a real-time model. Optimizing batches sequences. The objective of modeling is to determine the sequence of batches that should flow in the pipeline. For discrete time models, the result is a matrix, sections by periods, which indicate the batches that occupy each cell of the matrix. This implies that the mathematical model must establish the energy loss curve of the mixture, considering the operation of the pipeline, as presented in the diagram. Experiments conducted by Hy indicate that a linear combination, weighted by the volume of each product, is appropriate. Optimizing batches sequences. The batch sequence optimization problem is complicated by its combinatorial character, with precedence constraints. Precedence restrictions reduce the domain of combinatorics, since they do not allow all combinations. This facilitates the solution of the problem but leads to greater complexity in modeling. An example of this type constraints is the one that does not allow a product of lower quality and cost, like kerosene, to go in the previous batch to a product of high quality, like jet gasoline. This prevents contamination of products. These problems are of the MIP type, and can be solved by mathematical programming, or by the constraint programming. Hy has selected to work with mathematical programming. Temperature impact optimization. Impact of temperature in pumping oil products. Due to seasonal variation, the average line temperature may change in time and space. As it is shown in the next images, viscosity of crude oil is a strong function of API gravity and temperature. This affects the amount and the cost of energy, and the transport capacity. At very low temperatures the system may stop operating. To improve the precision of the operation, in the medium and short term, predictive artificial intelligence tools must be available, to incorporate their projections as part of the input parameters, of the optimization mathematical models. Variation F crude oil viscosity with OP and temperature. The figure shows that the oil viscosity decreases as the temperature increases. Lower viscosity results in higher Reynolds, therefore, the friction factor decreases. Effect of temperature on total pump power requirement. The analysis indicates that for an oil pipeline, the pumping power requirement varies as the crude oil degrees API changes. Increasing line average temperature reduces the crude oil viscosity. The reduction of viscosity results in higher Reynolds number, lower friction factor, and in effect lower pumping power requirements. 8 degrees Celsius of temperature difference can imply about 25% of difference in energy consumption. This impact is not limited to pipelines, it also affects production fields. Drag reduction optimization. Drag reduction is a physical phenomenon that causes friction to be reduced, and fluid flow to be increased. Chemicals that reduce drag are known as drag-reducing agents, DRA. Several polymeric compounds can reduce the wall shear stress of flowing liquids at low concentrations. Thus, the use of DRA has the following advantages. Increased pipeline capacity, the throughput. Savings in pumping power. Pressure reduction with the associated reductions in pipe thickness, and pressure surge, and reduction in pipe diameter in the design phase, as well as the number or size of pumping facilities. Drag reduction optimization is a nonlinear optimization process. This implies the determination of the optimal amount of DRA that must be injected into the oil products to optimize its transport, considering the cost of DRA at the injection site, the change in operating conditions, and the value of saved energy. The existence of DRA dates back 50 years, when Conoco Incorporated patented the product. Its first commercial use was in the Trans-Alaskan Pipeline in 1979, where a 50% drag reduction was achieved, thereby increasing the capacity of the pipeline from 1.45 to 2.1 Mbpd, Berger et al., 1982. This resulted in eliminating the need for installing 2 pumping stations, which were planned to achieve the mentioned increase in capacity. Since that time, the DRA have been used in many petroleum product pipeline installations. From a reference point of operation, the use of DRA can produce 2 effects. Reduction of the amount of energy required to transfer the batch volume, at the same transfer rate, lowering the cost of energy. Or increase the transfer rate, while maintaining the same energy consumption. Increasing pipeline capacity. The triangle defines the possibilities of operation. For a given level of DRA, the optimal solutions will be over the yellow line. This drag reduction optimization involves an empirical, experimental, process to determine the variations in operating conditions, pressure and flow, considering the conditions of the pipeline and the pumps, and the impact on the operation of the concentration in weight, and volume, of the type of DRA used. To do this, a model of the pipeline, a digital twin, must be built considering the theoretical mathematical equations of the flow, and validate them with the controlled measurements, using a model supported by artificial intelligence. Hy suggests a model based on the dual-state Kalman filter. The image presents the connectivity of a state estimation model, as part of the DRA function parameter estimation process. This is because there are no exact equations for its description. The benefits of DRA optimization are: increase pipeline throughput, reduce energy of pump stations, reduce pipeline flow friction, reduce carbon emissions, reduce operation pressure, save energy costs, increase technical and economical productivity, and increase transport capacity, then avoid construction and expansion of pipelines. Pipeline digital twin. The concept of the digital twin is associated with cyber physical systems, and provides an innovation that will bring a new look to industrial automation. However, the basic concepts of digital twins are old, and date back many years, in which models of differences, and finite elements, were used to build simulators of industrial, or natural processes, that would serve to support decision-making, and to validate the knowledge that we have of the process and reference. The big change given in Industry 4.0 is due to the ease of its implementation, which includes modern visualization that includes concepts of virtual reality, and augmented reality. Given the complexity of the problem, which means that precise approximations are required in the optimization model, it is convenient to have a detailed numerical model of the pipeline and the pump system, in order to verify several aspects of the integral problem. Quality of the solutions proposed by the optimization model, and an additional measurement system for predictive analytics models. The image presents the connectivity of a digital twin to support the state estimation and optimization models. In the past, Hy has built, in Excel, pipeline simulation models that maybe supports the digital twin of an oil pipeline. Politic tactical planning. Hy framework. The following graphic, taken from the Rajkowski and Pinto, 2005, illustrates the problem of planning politics, which has two fundamental aspects: sequence of batches, and hydraulic conditions. Along the polyduct. The planning of a polyduct aims to determine goals, not transport orders, for the transportation of oil refined products in the medium term, that is, in the order of weeks, or months. The results sought are defined goals for the sequence of batches to be dispatched and define their technical specifications, volume, transfers rates, and DRA injections. The time, period, of departure and of arrival of batches. The level of inventories at each terminal linked to the pipeline system. The operation plan of the pumping stations, and the minimum cost of the operation of the system. The complexity of the problem of programming the sequence of batches in a polyduct is evident, since it corresponds to a combinatorial problem that involves binary variables to coordinate the assignment of sequences to the different batches, which defines a MIP problem with NP-hard complexity. If the transfer rate is considered as a variable, the problem will become a MIP problem, which further complicates its solution. Three fundamental aspects must be considered in modeling: the nonlinearity that is generated in the movement of the batches, the no linearities in the pumping stations, which may be non-convex, and the rules that must satisfy the sequence of batches of the different products. Not all combinations are allowed. Hy's criterion is to maintain the model as a MIP optimization problem. In the movement of fluids in the pipeline system, the fundamental nonlinear equation defined that time of the displacement is equal to the volume transferred divided by the flow rate. In the fundamental equation, the three variables are part of the decision problem, which entails a nonlinearity that complicates the solution of the mathematical problem. The objective function must be considered to know the type of problem. It is assumed to be to minimize the cost of transport energy. The conversion of the transfer rate into energy implies another nonlinearity. If this function is continuous and has diminishing returns, the problem will be of convex programming. The mathematical modeling alternatives are: exactly implies a nonlinear model, and approximate, assuming discretized transfer rates. It implies a linear model. In this modeling, the transfer rate is obtained trough of a convex linear combination of all discretized transfer rates, which correspond to model parameters. The approximate movement of fluids implies the modeler select our transfer rates to simulate the flows in the model. It is equivalent to divide the line in our lines, each of them with a fixed transfer rate, which linearizes the problem for each line, and the effective transfer rate is calculated as a linear combination of each of the transfer rates. The lambda multipliers represent the fraction of the time during which the line operates at the associated flow. The approximation must be made for each line and applies to all sections that are flowing in the system during period t. This approach is appropriate when speed is required to obtain an approximate optimal solution, near to the real optimal solution. It is the case of tactical planning, but it is not the case of real-time scheduling. The high proposal for pumping station operations is to model the pumping system using a convex hull, calculated offline, which corresponds to a linear model. For those parts of the pumping operating system, which involve discontinuities, and therefore nonlinearities, it is suggested to make approximations, which guarantee convexity. Planning based on previous experiences. Discrete formulation of continuous process. Due to multiple limitations that existed in the past, for example, limited computing capacity, optimization algorithms in the process of growth, lack of knowledge of high-performance optimization methodologies, and difficulty formulating complex math problems. Approximate models were generated based not on an exact mathematical formulation, but on those aimed at selecting one, or a combination of solutions, proven, whose greatest quality is that they guarantee feasible solutions. For those old years, that was a wise way to face with the problem. This process is based on generating solutions to known scenarios, and formulating a simple optimization model, which ignores the constraints of the problem, since they are implicit in the solutions analyzed. This approach, now questionable, entails cost overruns due to its inability to generate optimal solutions. To analyze the impact of this approach, it considers that the green shaded zone represents the real feasibility zone of a continuous process. If a discrete formulation is used, that is, discrete solutions are assumed for continuous variables, the real feasibility zone will be reduced, affecting the optimization, so that the profits provided by the model will be seriously reduced, being able to reach zero. In the case of using a single solution, there will be no optimization, and the feasibility zone will be reduced to the point of the formula used. In the case of using two solutions, the feasibility zone will be reduced to the line that connects the 2 points that represent the formulas used. The solution shall be a point on the line that determines the convex linear combination of the two formulas. In the case of using 3 or more solutions, the feasibility zone will be reduced to an area delimited by the points associated with the formulas. The solution will be a point inside the modeled feasibility zone, which can be expressed as the area containing all the convex linear combinations of the formulas used. To the extent that discrete solutions are incorporated, the modeled feasibility zone will approach the real feasibility zone. The quality of the approximation depends on the coverage made by the discrete formulas of continuous space, something similar to what happens in the design of experiments. A greater number of points do not provide more information, if they fall into the area defined by the convex linear combination, defined by the extreme points of the historical sample. No more points are required, more coverage is required. In any case, the representation based on discrete formulas generates suboptimization, due to a smaller feasibility zone than the real one. There are large-scale optimization methodologies, such as Bender's theory, which starting from an approximate feasibility zone are forming the real feasibility zone, to achieve the optimal solution. In this case, the solutions what should be incorporated, are generated by an artificial intelligence based on mathematics, and not on the practices, or on the mental models, of humans. In concrete terms, sub-optimization implies lower ROI captured by mathematical models. Saving a little money in mathematical complexity but leaving important money on the table. It is a bad business. Case: optimization of scheduling of multi-product pipeline and depot inventory. The following is the summary of the paper, Simultaneous Scheduling of Multi-Product Pipeline Distribution and Depot Inventory Management for Petroleum Refinery. The scheduling model consists of three submodels: a pre-processing submodel for regulating new feeding pipeline slugs, a TM handling submodel, and a product pipeline distribution submodel with consideration of depot inventory management. The MPD DIM could handle the mixed interface of oil products appropriately and economically through blending and distillation operations. Meanwhile, the optimization of multi-product pipeline transportation and depot inventory management could be simultaneously accomplished. The efficacy of the methodology and MPD DIM model has been demonstrated by 6 case studies. The image shows a schematic diagram of multi-product distribution system. Continuous time modeling corresponds more to a scheduling model than to a planning model. The Gantt diagram presents the process of filling tanks at the terminals for the 3 types of refined products. The graphs show the inventory profiles of the transmix tanks of products in the warehouses. The tanks include blending tanks, tactical planning of a pipeline network, blending and transport. The integrated planning of a pipeline system that links different streams in the oil chain is the central part of the enterprise-wide optimization of an oil company. For a petroleum products transportation company, its business may be to efficiently transport petroleum products. But it can become more profitable, not to transport them. This is related to the definition of which is the product that is transported and marketed, oil and derived products that are physically transported, or the technical specifications that are transported in the products. Natural gas transport is a good example. All natural gases have different energy content. What is used in thermal power plants is energy. Natural gas is a medium that contains energy. Commercial agreements are made on quantities of energy, and not so much on volumes of gas. The technical, commercial, characteristics of the product depends on the type of oil product that is moving along the pipeline, and the blending of these products in the terminals of the pipelines. It could be the case of moving a product to a terminal, to complement the technical specifications of the existing products in the terminal, mix them and deliver them to the customer, depending on the commercial transaction. The problem discussed in this section focuses on the distribution and blending of oil produced in the fields, to be distributed to the terminals of the oil facilities, where it will be delivered for use in refineries, own or in other markets. Refineries are modeled in an aggregate way, as an exogenous demand for oil. On the other hand, there is the transport of derivative products. Integrated optimization of the entire oil blending chain implies a holistic model of the problem. This vision produces greater economic gains than its piecemeal modeling. The model blend allows to plan transportation operations for multiple oil production systems, with a view to delivering crude oil blends to refineries and/or ports that are connected to the system. The system accepts any type of connectivity topology between facilities. The supply of oil is given through fields producing different types of crude oil, with a predefined availability. This offer can be defined dynamically, considering the evolution of the oil-producing fields' operations plans. It is also possible to consider buying crude oil in the spot market. The demand for commercial crudes occurs in refineries and export ports. It is possible to buy crude oil in the spot market, in order to mix them and obtain new commercial oils. It can also be considered purchases or sales of oil futures, which must be respected. The purpose of optimization is to determine the optimal operation of the system, in such a way as to maximize the utility produced, or to minimize the costs of satisfy a predefined demand. A terminal can be conceptualized as a machine that takes multiple oil crudes, mixes them, and produces multiple blended crudes. There are also, at the end of the refinery, terminals oriented to handle the finished products and their blending. The image presents an example of the blending equations. The diagram presents the flow of materials in the petroleum system. The entities considered in the modeling are crude oil, oil field, oil terminal, tank, refinery, oil port, commercial oil, market, and regional market. An example is the modeling of an integrated system of production, consumption, distribution, and purchase, or sale of blending oil. The features of this system are: oil is produced in the production fields, each field being characterized by the type of oil it produces. Such oil must enter the oil distribution system that feeds export ports, through which commercial commitments to sell oil in the spot market, or the financial markets, or directly to the refineries. Optimizing the blend of crude oil and petroleum products is a multi-million-dollar application. It can be coupled to the production of oil fields, in such a way as to establish optimal plans for production, distribution, export and import. In addition, blending processes extend to petroleum products, for example, lubricants. A case of the optimization of crude oil blend scheduling is presented. The problem involves a pipeline, 2 receiver tanks, 2 cargo tanks and a pipe still. The table presents the batches of crude oil and the receipt and dispatch orders, including the tanks. The Gantt chart presents the crude oil mix schedule for a 10-day planning horizon. Reducing quality target variance should be at the top of the list for refinery improvements. Deviations from quality targets should be minimized, to charge the pipe still with a steady mixture of crude oil. Steadier quality crude oil mixtures charging the pipe stills will also translate into steadier operations for downstream production units. It also makes good sense to run pipe stills with a constant flow rate for as long as possible. An example of an improved quality target, or key planning proxy is shown in figure. Hypothetical benefit calculations. Total yearly savings in American dollars, quality target variability improvements such as whole crude oil sulfur, 2 million, reduced chemical injection, 100,000, distressed sale of crude oils from the refinery, 325,000, pipeline penalty charge for changes in sequence or timing, 75,000, spot opportunity for crude oil trades, 250,000, and reduced working capital, 100,000. Total year, 2,850,000. These hypothetical benefit calculations translate into over $2.5 million worth of the potential refinery profit that would not have been achieved with manual scheduling alone. It must be emphasized that this number only provides a benchmark or yardstick Pareto, at least qualitatively, the priorities in terms of choosing between other possible and competing capital investment projects at the refinery. From the perspective of overall crude oil costs of the refinery over 1 year, this $2.85 million in savings is less than 0.41% of the total feedstock cost. Oil and gas pipelines nominations and bilateral contracts. The nominations are the agreements made by the carrier and dispatcher to transport oil, natural gas, and petroleum products, using pipelines. This process normally occurs within a long, or medium-term contract, between the transporter and the dispatcher. In turn, the contract of the dispatcher, who can be a distributor, or a large consumer, is backed by contracts with end customers, and this process determines the demand for transport services that must be attended by the transport system operating company. Short glossary. Nomination, a request for a sender's transport service. Nominated quantity, refers to the volume that the sender requests to be transported from a point of receipt and delivered to a certain point of delivery. For a period of nomination, this must be authorized by the carrier. Nomination period, this is the period for which the dispatcher submits its transport nomination request. Cycle, subperiods into which the nomination period is divided. For example, days, weeks, fortnights, etc. Period, represents the period to be nominated, month, week, day, or another period agreed between carrier and dispatcher. The image shows a oil and gas pipelines nomination example. Mathematical modeling. The nominations have several relationships with mathematical modeling, namely, short term, determine the demand for transport services that the carrier has accepted and authorized, normally assumed as an input data, that is not affected by the real-time or short-term model. Medium-term, tactical planning, depending on the agreements between carrier and dispatcher, the medium-term model, of the order of months, week, days, can adjust the nominal transport plan, to optimize the economic benefits, and to improve the technical conditions of the operations, and long-term, strategic planning, this modeling can be related to long-term contracts. They can be used to accept the contract, verifying the required transport capacity, and definition of the price, or the marginal costs associated with attending the long-term contract. At the end of the last decade of the last century, Oil Express, a global natural gas company, that operated several natural gas producing fields in multiple countries, asked Hy for support to define a natural gas field exploitation planning strategy, using highly complex mathematical models, to analyze the entire decision-making environment. The challenge was to develop a model that supported the decision-making, regarding the exploitation of natural gas field, and its impact on Oil Express finances. Oil Express, Natural Gas Field Exploitation Planning. In 1997. Analysis of the gas market for the electricity sector. The main study carried out with Hy Power was the analysis of the national gas market for the electricity sector. This is due to no alternative markets for natural gas other than national electricity generation. Pressure from the electricity regulator, to sign contracts by generators and producers of natural gas, for the purchase and the transportation of natural gas, to give firmness to the electricity sector. Oil Express fundamental hypothesis: if the gas market is not sustainable, it makes no sense to sign bilateral contracts with electricity generators, and to invest in extracting the natural gas, and the optimal strategy is to wait for the right moment in the future. The analysis was carried out using take-or-pay contracts as a basis. The take-or-pay, TOP, is a contractual clause, requiring the buyer to take the delivery of a specific amount of goods or services, from the seller or pay a fine if they do not. Thus, it protects the seller against potential losses if the buyer refuses to complete the purchase by a particular date. A top clause is common in energy industries, including oil, natural gas, mineral, and coal, seeking significant investment. It is also called the kill clause. The contract is normally signed before the companies start oil, natural gas, minerals, or coal exploration. Therefore, it is a type of offtake agreement. A top clause is common in energy industries, including oil, natural gas, mineral, and coal, seeking significant investment. It is also called the kill clause. The contract is normally signed before the companies start oil, natural gas, minerals, or coal exploration. Therefore, it is a type of offtake agreement. Fuel supply contracts directly affect dispatch. In general, a contract has the following components. A percentage of the maximum consumption is purchased in the take-or-pay mode. The surplus over the take-or-pay is purchased under the pay-as-you-go modality, and there is a rolling period to consume the take-or-pay part. Given the seasonality of prices in the electricity sector, the model included top with a rolling period, which gives flexibility to the buyer to accommodate their physical purchases. But it complicates the generator decision-making process. To stimulate the natural gas market for the electricity sector, government institutions conducted a reference study. This study was taken as a reference to analyze the market using the SHTG model. The main characteristics of the study was: the rolling period was 6 months. 10 plants were considered for take-or-pay contracts with an installed capacity of 2,813 megawatts. The take-or-pay percentage was 30% for the plants of the center and 70% for the plants in the border, and the electricity dispatch planning model used by ISO operator was adapted to represent the impact of TOPS. The table presents the summary of the characteristics of the scenario, studied by the regulator to stimulate the signing of contracts in the natural gas market. The percentages of TOPS fixed do not come from an optimization model, they were perceptions of what should be. The chain of qualitative effects, which derive from top contracts, is relatively easy to foresee. The bid price of the thermal plants to the spot market will go down. This is because they have turned the variable cost into a sunk cost. In the extreme, it could reach zero. This will lead to an increase in the dispatch capacity of thermal plants, and the fall in spot prices. But quantitative effects, they're not intuitive, they can't be calculated with an Excel spreadsheet. As the volume of natural gas contracted through TOPS increases, it can be expected that hydro plants will lose share, thermal plants will gain participation, and the spot price go down. It is clear an economical resource, but not 100% reliable, hydroelectric energy, is being exchanged for another more expensive but more reliable, thermal energy. It should be considered as a risk premium. From the point of view of income, we have revenues from hydro generators will decrease, and the change in the income of thermal generators cannot be evaluated a priori. Therefore, a mathematical model is required to evaluate quantitatively the natural gas market. Modeling take-or-pay contracts. To carry out the study, 5 cases were implemented to consider the top modeling. The following is the code associated with the modeling and description. No top, no contracts. Libre, optimized contract generation. Equations are included in the dispatch model, high power, to accurately represent top contracts. Rodante, minimum rolling generation. The minimum generation of the thermal plant is forced during the rolling period, to ensure compliance with the contract. Mensual, minimum monthly generation. The minimum monthly generation of the thermal plant is forced, to ensure compliance with the contract. More restrictive than the previous one, and MWKTE, fixed generation at the base. The thermal plant is forced to generate in the base, permanently, to ensure compliance with the contract. More restrictive than the previous one. All forced generations can be implemented with an economical dispatch model, without requiring modifications to the model. All these imply losses for thermal plants, when the marginal costs of electricity are below the variable cost of top. Top contract modeling implies dividing the thermal generation in GT0 thermal generation with cost equal to variable OM costs excluding fuel cost. Typo 0, limited by top contract, and GT1 thermal generation with cost equal to variable OM costs plus fuel cost. Type 1, non-top contract. GT, the total thermal generation, must be equal to GT0 plus GT1. There is only one appropriate way to study top contracts, and in general any bilateral contract. Model the operations and the financial transactions as they are described in the contract. Approximations to this modeling will only bring economic losses for the generators and for the society. For example, trying to adapt an economic dispatch model, by parameterizing the dispatch of thermal plants, will bring negative consequences for all market agents. All forced generations can be implemented with an economical dispatch model, without requiring modifications to the model. But all these imply losses for thermal plants, when the marginal costs of electricity are below the variable cost of top. To quantify the financial impact of take-or-pay contracts, we can consider the estimated operating income for generators, defined as the marginal cost, a proxy of the spot price, multiplied by the generation. Since the spot price goes down due to the top, the highest value reference is the market with no contracts. In this case, for simplicity, the post-optimization financial impact has been evaluated, using the resulting dual variables as a reference. However, it should be noted that high power can solve an PEC, mathematical problem with equilibrium constraints, problem in order to convert the financial impact into part of the optimization model, and thus obtain a more accurate view of the health of the market. Scenario aggregate economic results. Following the logic, the most economical option is not to consider the top contracts. When including the top, a risk premium must be assumed, which could be established as the difference between optimized contract generation and no top contracts. In this case it implies 26% of cost overruns. The last 3 cases involve overcosts due to the poor quality of mathematical modeling. As poor quality increases, cost overruns increase. It must be interpreted that if we implement low quality models, This will translate into more expensive operations, which will pay someone in the market. The first candidate is the user of the models. The effect for hydraulic generators, which generate less, and receive less remuneration for each MWH generated, the negative effect is evident. For thermal generators with top, the increase in generation could be produced a higher operating income. The impact can be summarized as: top contracts as proposed adversely affect the aggregate of all generators, and when mathematical modeling practices are incipient, this will negatively affect the market. A good way to present the financial information is the accumulated curve of estimated operating income over the entire planning horizon. The graph shows operating income of hydraulic generators. These graphs presented the aggregation of all generators, but they exist for each individual generator. In the case of this hydro generator, paradoxically its financial health does not depend on its actions, but on that of other agents. If thermal generators assume a rational position, the financial health of the hydro generator will not be affected. But, if they assume an irrational position, ignoring mathematical laws, the hydro generator can go bankrupt. In simple terms, this defines an externality undesirable in a market, in which the errors of an agent can be paid by other agents. The golden rule is everyone pays for its own mistakes and takes advantage of their right decisions. The situation of thermal generators is different. For the planning period analyzed, the costs of top contracts cannot be recovered. The financial damage will be greater if the decision handling is not based on specialized mathematical management models. The graph indicates a general crisis of the thermal generators, if the top indicated by the government are signed. The graph shows that the financial health of a specific thermal generator may depend on its management capacity, and that if there is an exit, the generator can become profitable in a market in difficulties. High Power allows Oil Express to financially analyze all market participants, both potential customers and clients of the competitors, which allows Oil Express to perform the scientific market intelligence activities. Considering that the proposal of tops made by government entities does not come from an optimization process, but were defined considering logic and good practices, Hale and Oil Express proceeded to make an adjustment in the value of the tops, so that they approached an optimal value, and thus analyze the behavior of the market in these conditions. These adjusted values do not come from an optimization process. However, it should be noted that the high power model can be used to determine optimal top values. The graph presents the comparison of the results for the cost recovery of hydraulic generators. Values set based on mental rules can affect the market, even bankrupting it. It could be concluded that the greatest damage that can be done to the market is to establish reference values without justified mathematical support. Since there are values of the tops that minimize the values of the risk premiums for reliability, without profoundly altering the economic behavior of the market. It is coherent that if the thermal generators act rationally, they do not drastically affect the hydraulic generators as a consequence of their bad decisions. In the case of cost recovery of thermal generators, the situation is more complicated, due including the optimal values for the tops will generate problems of bankruptcy and liquidity, which will be more serious if the top values do not have an appropriate rationality. This indicates that the electricity market cannot guarantee that thermal generators can pay the top contracts that are theoretically required by the government. The model turned out to be correct, since in early 1998 it detected the market crisis between 1998 and 2000, which led to bankruptcies of thermal generation companies. Successful decisions. For its part, Oil Express has proven that there are no market conditions, that is, do not exist a good set profitable thermal generators that can pay for gas through TOPS contracts, required to guarantee the extraction of natural gas. If it is a question of compensating the situation based on price, if Oil Express sells natural gas at high prices, it is possible that Oil Express must recover bankrupt industrial company assets. Everything seems to indicate that the optimal decision may be to delay the investment, waiting for a market with better conditions. Successful decisions. For its part, Oil Express has proven that there are no market conditions, that is, do not exist a good set profitable thermal generators that can pay for gas through TOPS contracts, required to guarantee the extraction of natural gas. If it is a question of compensating the situation based on price, if Oil Express sells natural gas at high prices, it is possible that Oil Express must recover bankrupt industrial company assets. Everything seems to indicate that the optimal decision may be to delay the investment, waiting for a market with better conditions. Oil pipeline scheduling. The white paper Oil Pipelines Real_Time Optimization contains the detailed information about the model described in this section. The work carried out by HI is the result of the empirical analysis of multiple implementation alternatives for the solution of the problem associated with the optimal operation of an oil pipeline system, ensuring that the methodology implemented complies with. To respect detailed hydraulic modeling of the pipeline system and pumping station system. To manage electricity rate schemes differentiated by time slots. The planning horizon is 72 hours of operation with a 10-minute breakdown. The first version of the model ran on a personal computer in 2012. The input data of the mathematical model is lengths, diameters, thicknesses of pipes, mechanical strength, internal roughness, etc. Elevation profile of the lines. Properties of main elements in each station, pumping units, control valves, load curves, efficiency, stages, NPSH, BHP, etc. Maximum and minimum pressures at various points. Energy costs, schedules, where applicable, self-generation, fuels required. Detailed transportation program for a maximum period of 72 hours. Default sequence of tenders and their volumes. Delivery times, and physical properties of products, density, viscosity. HI has developed an optimization mathematical model for real-time scheduling of oil pipelines. The process involved the following experimentation stages. Implementation of a MINP integrated model to try to solve the problem directly. Implementation of a multi-level model based on the principles of relaxation/Lagrangian coordination. Basic models with MIP or MINP formats, and implementation of a multi-level model with preprocessing based on interpolation principles through convex linear combinations of optimal preprocessed solutions for pumping stations. Basic model in MIP format. Cyclic movements based on gradients. Multi-level model based in a mix of methodologies. The strategy is based on 4 stages and 7 optimization models, which are solved using Lagrangian model coordination methodologies. The first stage is the offline preprocessing, which consists of 3 processes. 2-dimensional flow pressure surfaces, convex or non-convex hull, of optimal energy consumption, and the corresponding configuration at each pumping station, to meet a flow rate Q at a pressure P, for each type of crude oil. Definition of the 2-dimensional feasibility zone, Q, P, of the operation in the pumping station for each type of crude oil, and definition of the detailed hydraulic behavior of friction and gravity pressure loss in the pipeline system. This information comes from the expert system, that stores the operating patterns of all pumping stations for all oil products. The second stage is the online preprocessing, that focuses on the domain reduction of the possibilities in the pipes. Determines the possible batches that can pass through a J section during a period T. In this way, the dimensionality of the model is reduced, since only the feasible tender section period combinations are considered, and this preprocessing depends on the data of the run, and must be done before starting the optimization process. The third stage is the optimization loop. The optimization process is divided into 2 steps, to decrease the dimensionality of combinatorial problems. The first step has 3 sub-steps. It ignores the displacement of the tenders along the system, and therefore approximates the friction losses in the sections in the different periods, which are calculated based on an estimated curve, that is assumed to reflect the characteristics of the tenders that is passing through the section during a period. It simultaneously considers all the periods of the planning horizon, and all the sections of the pipeline system, in order to obtain an optimal solution, ensuring that the pressure constraints are met along the pipeline system, and the flow of products through the pumping stations is detailed, that is, it considers for each period the tenders that are passing through the station. The second step has 3 sub-steps. It determines the displacement of tenders along the pipeline system, thus determining which tenders are passing through each section for each period, and based on the above information, it is determined which is the best curve of friction losses that represent what happens in a period for each section. This information is fed back to the first step. The problem process of determining energy losses in pipelines corresponds to a separable process, and therefore can be solved in parallel for every period of the planning horizon. Once the iterative optimization process has been stopped, the fourth stage is post-processing, and it is related to optimization of pumping stations operation. It has two steps. The algorithm proceeds to review for each period, and for each pumping station, the optimal conditions of the operation, according to the flow pressure pairs established as optimal scheduling, and the algorithm corrects the approximation that is generated due to the size of the grid that is used to linearize the optimal consumption in the optimization loop step, since during this process the problem is solved for exact values of the pumping plan, not for values of the grid limits. The image shows the optimization loop flowchart. Computational solution. The current state of the computer technologies involves the integration of edge computing and cloud computing to implement systems with multiple highly complex mathematical models that can be run in parallel. The implemented solution involves two phases of computer operation. Offline, it occurs when computers are not engaged in the optimization process and are dedicated to generating information that will be used on the next occasion that is required to optimize. During this phase operate tasks related to generation of convex hulls, and generation of information related to predictive analytics methodologies. Online, it occurs when computers must meet the immediate demand for optimization processes. In this phase, computational resources are oriented to autonomous real-time distributed optimization, using in parallel large-scale methodologies to solve the problem. The offline convex hull generation is a semi-automatic process, which must be performed when new products are going to be incorporated into the pipeline. It can be carried out in parallel, since strictly each point of the grid can be optimized independently for each product in each pumping station. However, the chain sequential optimization of a product in a station can take advantage of an optimization process that considers how the grid is covered. The online optimization is a process that in its first part is not parallelizable. This is because displacement of all tenders are intertwined. The adjustment of the operation of the pumping stations is parallelizable, which can accelerate the final optimization when the number of periods of the planning horizon is large, that is, when the duration of the periods tends to zero. This is typical of optimal control models. All the processed information is stored in an expert system supported by a relational database that stores all the results of the optimization processes carried out. The implementation of the models was realized using Optex Expert Optimization System. Optex is the high artificial intelligence that manufactures decision support systems for Industry 4.0. To solve the problem, a set of GAMS programs were implemented. The main characteristics are basic solvers, linear mixed programming, IBM CLEX, Gurobi, and or Express, and nonlinear programming, CONOPT. At the request of the end user, the system was implemented in an Excel interface, from which the operator performs programming and analyzes the results. HI has a solution accessing to a SQL-type database, Oracle, DB2, MySQL, etc., and the results of the optimization model were validated by comparing them to a perfect model that represents the real operating conditions of the pipeline. The structure of the implementation is shown in the image. The user interface has two parts: access to the information system and control of execution. The screenshot presents the header of one of the GAMS programs. The screenshot presents a shell window containing the master table of pumping stations, and 4 data windows containing tables related to that master. These tables are in a SQL database. The screenshot presents a shell window containing the master table of pumping stations, and 4 data windows containing tables related to that master. These tables are in a SQL database. The screenshot presents a shell window containing the master table of pumping patterns, and the data window containing the table related to the patterns. Image shows an example of the pump configuration BPC 701. Image shows another of an example pump configuration BPC 701, using 3 pumps. Case: Oil Express Pipeline Real-Time Optimization. Case: Oil Express. Description: The Oil Express pipeline is composed of 2 pumping stations and a maritime terminal, FSO terminal. The crude oil is stored in tanks and then transported by the submarine pipeline to the floating oil storage unit for the loading of the tankers. PSO2 pumping station in charge of giving more pressure to the 20,000 barrels oil that are received per hour from the PSO1 station and that are sent to the FSO maritime terminal. PSO1 pumping station receives crude oil from the fields located near to the station and from other oil pipeline. From this station, the crude for domestic consumption is driven to an oil express refinery and to exportation using the FSO maritime terminal. The image presents the profile of the oil express pipeline. To ensure the quality of the results, it is necessary to connect a hydraulic simulation model of the pipeline system with a hydraulic simulation model in the optimization model. This process has the following steps. Calibration of the simulation model, which represents the pipeline in full detail. This model must be calibrated against reality. The result of the model is presented in tables. The model in table format is not easy to incorporate into the optimization model. An alternative is to convert the table into a continuous model, using a regression model. These 2 models are run offline, and their results can be stored in the offline database. The results of pipeline approximate regression continuous simulation model must be compared with the original simulation model. The main objective of the simulation model is to validate the accuracy of the hydraulic model, pumping stations and pipes, which will be used in the optimization model. The table presents 4 of the comparisons made, for pressure flow pairs, for heavy crude oil, at the PSO1 pumping station. The mean error for energy consumption was 0.23%. The optimization hydraulic model is solved online by the real-time optimization model. The main objective of the simulation model is to validate the accuracy of the hydraulic model, pumping stations and pipes, which will be used in the optimization model. The table presents 4 of the comparisons made, for pressure flow pairs, for heavy crude oil, at the PSO1 pumping station. The mean error for energy consumption was 0.23%. Case: Oil Express. List of variables and models. The optimization process has been divided into 3 sequential stages, to solve the problem in parts, reducing as much as possible the process time required each time the models need to be run, to define a new pumping plan. The 3 stages are: Pre-processing involves the analysis of information from the pipeline system, with a view to preventing the optimization model from repeating calculations that can be performed in advance, and whose results may be permanent, with the aim of minimizing the time to solution. 2 types of pre-processing are considered. Offline, before starting the optimization process, to calculate parameters that are independent of the operating scenario, and online, before starting the optimization, but when the optimization scenario has been defined. Optimization: every time a pumping plan is required, 72-hour planning of the operation of the pumping stations, an optimization problem must be solved, which has been divided into 3 processes to control its dimensionality and solve it in the shortest possible time. Post-processing, aimed at defining details of the problem that may have been approximated during the solution of the optimization model. The table presents the indexes used in the model, which correspond to the entities, or objects, of the information system. For all these entities, a master table must be created, and all tables that define the relationships between entities. The table presents the variables of the CTLN model for convex hull generation. Case: Oil Express. Real scenario results. The graph presents the costs of the energy used in pumping stations. Pumps 2 and 3 use fuel oil, pump 1 uses electricity. The electric power cost changes during the day, considering the hourly seasonality of energy demand. As it can see at 1900 hours there is a peak in the cost of electricity. Within the feasible operation zone, area within the blue lines, two types of configuration can be presented to achieve a dispatch of 6 kbph. These are Caucasia to the step, red line, or Caucasia in redispatch, green line. In the table, the hourly report that produces the model for each pumping station is presented. It is concluded that, due to the high cost of electricity, shown in the previous graph, at 7 p.m. there is a pumping stop at the PSO1 station. The table presents the results for stations PSO1 and PSO2. The table presents the report by pump. It contains the name of the station, the type of pump that operates, the discharge pressure of the station. This is discharge pressure of the pump minus control valve, the power consumed by the pump, the efficiency, and the RPM at which it is operating, and the cost of energy at the pump for that hour. The hourly report presents the dispatch at each station, that is the crude oil being transferred, the optimal pattern, and the amount of product shipped. For example, at 1500 hours, two types of crude oil are being dispatched at the PSO1 station. The report presents the pressure for each section, inlet and outlet, friction losses, gravity losses, and length. The graph presents the different components of the pipeline's energy profile. The table presents the movement of batches along the pipeline. For each hour, it is indicated in each section, the batch that is passing. To compare pipeline operation policies, two experiments were conducted: economic policy, minimization of the cost of operation, green line, and environmental, minimization of energy consumed, blue line. The graph presents the results for the flow profile. There is a stop at the pumping station, PSO1. The stop in the minimum energy consumption policy is due to the minimum pumping flow in the station, since, if possible, the optimal policy should be to maintain fixed the flow around 5 kg per hour. In the case of the minimum cost policy, fluctuations in flow are due to variations in electricity prices. The graph shows the pressure profile at the PSO1 station. Comparing the results of the objective function of the two operating policies, it can be observed. The minimum energy policy generates 16.21% of overcost, and the minimum cost policy generates 19.43% of overconsumption. As you can see, the differences are not negligible, and are a measure of the precision that mathematical models can provide when solving real-life problems. Estimating this difference based on good practices and/or mental models is practically impossible. Homeland Security. Case: Defending Critical Infrastructure. This section is based on the paper Defending Critical Infrastructure. In 2002, the USA Department of Homeland Security deems 13 infrastructure sectors that must be protected: agriculture, banking and finance, chemical industry, defense industrial base, emergency services, energy, food, government, information and telecommunications, postal and shipping, public health, transportation, and water. Critical infrastructure protection. Development of tools to anticipate, identify, and measure the risks to which a nation or region's critical infrastructure is exposed. This is to reduce the risks and consequences of an attack. B-level and tri-level optimization models to make critical infrastructure more resilient against terrorist attacks are used. Each model features an intelligent attacker, terrorists, and a defender, us, information transparency, and sequential actions by attacker and defender. 3 real examples are presented. The U.S. Strategic Petroleum Reserve, the U.S. Border Patrol at Yuma, Arizona, and an electrical transmission system. Each exercise gathers open-source data on a real-world infrastructure system, develops an appropriate B-level or tri-level model, and uses these to identify vulnerabilities in the system, or to plan an optimal defense. Only the first case is discussed in this presentation. Attacker and defender models. The core of an attacker-defender model is an optimization model of an infrastructure system whose objective represents the system's value or cost to the defender, our society, while it operates. For instance, the maximum throughput of a pipeline network could measure that system's value, while power generation costs, plus economic losses resulting from unmet demand, could measure the cost of operating an electric power grid. Attacker-defender model. It is assumed that the defender operates a system to minimize cost, which is represented by an objective function. The defender is a misnomer in these models, because the models do not directly represent defensive actions. Call it system operator would be more accurate, but awkward. The model posits that an attacker wishes to maximize the worst damage he can cause, by restricting the defender's operational activities. The attacker determines an attack plan, AP, in which he specifies which assets of the defender he will attack. Attacking an asset prevents the defender from carrying out activities that depend directly on that asset. To determine the set of activities included in the AP, the attacker solves the optimization problem, AD, that is a type of B-level program. A B-level program is a type of Stackelberg game. Here, the terms leader and follower in a Stackelberg game represent our attacker and defender, respectively. Defender-attacker-defender model. The solution of an AD model identifies the most critical set of assets for a system. To approximate the solution to the optimal defense problem, for example, to identify a near-optimal defense plan, given a limited defense budget, it is possible to solve a defender-attacker DA model considering the solution to the AD model. But how do we identify the truly optimal solutions? In theory, we simply embed the two-level AD model into a three-level defender-attacker-defender DAD model, which corresponds to a bi-level problem with a lower, internal, level that corresponds to the AD model with a restricted set of attack strategies. Therefore, the defender wants to identify an optimal defense plan so that when the attacker resolves AD, the benefit that the attacker perceives, i.e., the worst damage that the attacker can inflict, is minimized. Those interested in delving deeper into this topic are invited to watch the video. Homeland Security defending oil and gas critical infrastructure. Optimal design and planning of oil and gas supply chains. Financial analysis. The Decision Support System, DSS, for design and planning of industrial supply chains will be called SCD. SCD must be made up of multiple models that interact with each other. Models may be solved in two ways. Coordinated, independent models that share results with each other, according to a logical data flow. Integrated, the models are integrated into a single mathematical model, that is solved as a single mathematical problem. The best way is integrated, considering that it can solve the holistic optimization model, until it reaches the optimal solution. The first model will be called LogFin. It is oriented to define the investments to be made in infrastructure necessary for production. It corresponds to a dynamic model that defines, for each period of the planning horizon, the investments to be made, and the network for short-term operation. As input parameters, it should consider the costs of investment, rate of return on capital, the costs of loans, payment period, and other financial considerations. Model constraints are related to investment logistics and financial risks. The main results of the model are NPV, net present value, of the investments, VAR, value at risk, cash flow, and network design for the first periods. The second model will be called SANDOP. It is aimed at simulating industrial operations, for each possible network proposed by the investment model, LogFin. As input parameters it should consider, at least, the forecast of demand of final products, raw material supply operational costs, and sell prices. The model can be extended to consider other aspects such as technological innovation, that affects the productivity of processes, new technologies, which may affect market prices, and others that are considered convenient. In general, all input parameters are uncertain, and it is appropriate to consider that this makes a stochastic programming model based on scenarios. This characteristic makes the LogFin model a coordinator of the evaluation of the scenarios to be considered in SANDOP. It corresponds to a dynamic model that defines, for each period of the planning horizon, the industrial operations, and the storages of materials. In certain cases, it may not be necessary to consider product storage, because it may have little impact on investment costs, and additionally, it may be considered that its offer is always provided by the market with stable prices. This is not the case for oil storage, where the market prices and the supply of oil and gas is uncertain with high volatility. The constraints of the model are related to the industrial production process. Normally, there are several alternatives to simulate this process. At one extreme, we may formulate a very simple model, perhaps a few aggregate equations, that synthesize the process. At the other extreme, we may formulate a detailed model that simulates the processes with great certainty. The decision is of the modeler. What is true is that the available computer technology, computers plus solvers, allows very advanced models in this aspect. Therefore, the level of detail will grow exponentially in the next years. The main result of the model is the operational simulation for each period for each scenario. Data that are necessary to evaluate the future cost function, that generate the decisions of the present. The third model will be called ALM. Its objective is to simulate the assets and liabilities management, ALM, considering the results provided by LogFin and SandOp models. ALM is a modeling consolidated methodology that focuses on the financial modeling of companies. Its growth is generated at the end of the past century, in the financial sector, as a result of the Basel Accords. The minimum ALM modeling should be oriented to evaluate the NPV, for a pre-established ROI, return of investments. It will provide the financial statements, balance sheet of assets, liabilities and equity, income statement, profit and loss, after tax, royalties, and other contributions, and cash flow. Extended ALM modeling may include investments in alternative assets and liabilities, payment of dividends, capital repatriations, capital flow, and multiple currencies. In healthy logic, this model must be the coordinator of the holistic investment process, since it is the financial vice presidencies of the organizations responsible for endorsing investments in production assets. The results of the holistic optimization process are probability distribution functions for the primal variables and the dual variables of all DSS models. For example, the NPV. In simpler modeling, these distribution functions are obtained using spreadsheet simulation models. The results are not comparable because of the methodological difference in the approach. Success case: China National Petroleum Corporation. The paper operations research enables better planning of natural gas presents the use of mathematical optimization models for pipeline planning. China's natural gas consumption has nearly doubled in the past 5 years. To better meet demand, the China National Petroleum Corporation, CNPC, China's largest producer and supplier of oil and natural gas, partnered with researchers from the University of California in Berkeley and Tsinghua University in Beijing to apply operations research to develop and implement new software to help CNPC to improve the management of its pipeline network. Previously, all pipeline production and construction planning for CNPC, which controls 72% of the country's natural gas resources and 70% of its pipeline network, was done by traditional methods using spreadsheets. However, due to the increasing size and complexity of the network, the use of the traditional method resulted in excessive costs and wasted resources. Since implementing the new software, which uses a 3-stage convex relaxation method and iterative piecewise linear approximation methods, in late 2014, CNPC has obtained approximately $530 million of American dollars in increased earnings, 2015 to 2017. In addition, the resulting increase in the efficiency of the existing pipeline network allowed the company to postpone the addition of new pipes, leading to an official budget reduction of more than $20 billion of American dollars in construction costs for the following 5 years. The image present the algebraic formulation of the natural gas pipeline transmission model. Without fear of being wrong, it can be said that mathematical optimization models are the goose that lays the golden eggs of China National Petroleum Corporation. Like Herbert Simon, Hypothalamus Artificial Intelligence believes that the computer-based mathematical modeling is the greatest invention of all times. Thank you for your attention.